Welcome to part 2 of part 5 from the calculus of polar using integration. So in the previous lesson we found out we derived the equation for integrating for area of a polar function, which of course came from the area of a circle and using d theta and very small theta values from one theta point to the other to find the area. So now we'll do some examples. So taking this, area equals 1/2 integral from theta 1 to theta 2 of r squared d theta. We will find the area of the function we had earlier. R theta is equal to 2 plus 2 cosine theta. So I will graph it over here. And the graph looks somewhat like this. So let's say we wanted the area of just the top section here. Now, the first thing to look out for is what are my bounds. Now remember that since polar rotates, your bounds will not be from this value to the outer edge here, this value. It's going to be from whatever angle gets you from this value to the center and not crossing into the negative r values. So we know that the domain of this particular function is from 0 to 2 pi, since we start at 0 and we end at the same spot at 2 pi radians. So we can take half of that and we'd get half of the domain, which would be from 0 to pi, which would be from here rotating to the origin. Okay, so we're going to use that as our theta 1 and theta 2, 0 and pi, because again, that's where we rotate from the beginning to the origin here. That's the area we want. So we're going to say the area is equal to 1/2 integral from 0 to pi of r, so 2 quantity 2 plus 2 cosine theta, quantity squared d theta. And if we were to do that in the calculator, we would get we would get 9.425, I believe. Yes, okay. 9.425. Now, let's say we wanted the area of the entire cardioid. Now, there's multiple methods of doing this. So, one method, of course, is just doing the same integral here, but going from 0 to 2 pi. But we won't have to do that because there's an easier method, and that is taking advantage of the symmetry of most polar graphs. Most polar graphs you'll see will be symmetric because when they go around to each value, each radian, it's going to be the same but reflected in the negative direction or the positive direction, depending on where you start. So we can simply take this, what we had before, right over here. We can take area is equal to 1/2. Area is equal to 1/2 integral from 0 to pi of r theta squared d theta. We can simply take what we had before, but multiply the front here by 2, and we'll get the area of the entire cardioid, which would simply be 2 times 9.425. And we could also take the answer we got from that particular integral and just simply multiply it by 2, and we get the same answer here. And of course, this is because of the symmetry of the cardioid we have here.